All right, I'm going to pause there and I'll jump back over here. All right, I hope that at least gave you some good visuals of what some of the field work was like. I'll get to that a little later in the talk, but I think it's nice to start with at least some image of what I'm doing and what it's like down there, set to silly music, but it's fun. I get a kick out of it. So maybe to back up a little bit and just introduce myself. So I'm Dan Morgan. I grew up in the West Coast. So I grew up in Portland, Oregon. I was an undergraduate down in Southern California in a small school called Pomona College in Claremont, California. And then I took a gap year. I lived in a ski town and worked in a coffee shop and was basically a ski bum for a year. And then I went to grad school at the University of Washington up in Seattle, Washington. And then I finished up my PhD in 2009, and then I've been at Vanderbilt ever since. And ultimately, you know, as an undergraduate, I kind of stumbled into geology as a major. It's not something that I really knew anything about before I went to college. And honestly, I only took a class because a friend of mine in the fall said, hey, I've heard this professor's really good. Let's take his intro course in the spring. And so I took a class in the spring just because I wanted to take a class with my friend and ended up really falling in love with the subject. And then what I kind of discovered as I took lots of classes and got exposed to more things is that I really like studying landscapes, things like how do rivers create landscapes, how do landslides happen and create landscapes, and ultimately how do glaciers carve out and create landscapes. And what I think is really interesting is how, as things like climate changes, well, different landscapes get created as a result of that. And that you can see the history of the Earth and how it's recorded and how landscapes have changed over time. And that's ultimately the thing that the subfield of Earth science that really connected with me. And then I get to do field work all over the world. I often am going up to sort of high mountain places where there are lots of glaciers. I get to do work down in Antarctica, but I've also been down doing work in New Zealand. I was out in California fairly recently too, Peru, Nepal, Iceland, Italy. We were in Italy last summer before, when you could still travel to Italy, we were able to get out there. So it's fun, and I do get to do a lot of travel. And then I thought I'd also say a little bit about, you know, what do I do here on campus? So I have many roles and I get to do lots of different things. Again, I tease that I have a puppy brain. I'm easily distracted and like to do lots of different things. But I'm one of the associate deans for the College of Arts and Science, which means that I get to work with students in a variety of different things and help develop curriculum from a variety of different things. Mostly what I get to do, I get to run a lot of our honors programs here in Vanderbilt. So departmental honors, we have a small honors program called the College Scholars. I get to work with our merit scholarship students. And then I also do a lot of things that relate to a new academic initiative that we call an immersion project, which is basically that every student now in all of the schools has to do some kind of research or study abroad or internship or service project while they're here. And that's true of all of the undergraduates now. And it's fun to build that curriculum and work with faculty and students to create that while we're here. As you'll see, getting students research opportunities and the opportunity to do their own projects is something I really believe in. It's one reason why I really like working with the School for Science and Math at Vanderbilt. So then I teach and do research in earth and environmental sciences. So I'm what's called a principal senior lecturer here. And so I'm teaching a class for the earth science majors right now. And that's a lot of fun. I enjoy teaching a lot. I have run a lab here and I'm doing as much research as I can this semester. It's been a little hard, as you can imagine. And then I also put up on here, I'm no longer living on campus, but I was living on campus for 2 years as what we call a faculty head of house. And so my whole family and I lived in an apartment with about 80 students in the dorm for 2 years over there on the Commons, which is fairly close to where you all are. And it's something we really enjoyed. My 2 kids really liked being on campus and eating in the dining hall and going to all the events. And certainly, blending the kind of living learning experiences that you can do when you do that and recognizing that you're going to learn so much outside of the classroom and from your peers in college, but being able to blend some academic things in there, but also some personal development things in there is something that, as an educator, I really like teaching college students because you're able to blend those things. I'm able to teach students in the classroom, but also outside of the classroom. That's something I really enjoy doing. So you can probably hear my puppy growling at his toy over here, which is better than having him chew on me, I suppose. But sorry about that. So then before I jump into this, I definitely want to recognize all of the different collaborators that have worked on this project with me. As you probably got a sense of that from the video, there are a lot of people that work to make a project happen in Antarctica. And so it's worth acknowledging all the people that are doing that. And so the funding comes from the National Science Foundation, and the whole U.S. Antarctic program is doing things. Give me 1 second here. This puppy is too much. All right, sorry about that. You needed more distractions. The joy of doing these from home. So anyway, you can see the list of students that have worked with me. You'll see a couple of SSMV students up there. Lucia and Ruby have worked with me on projects related to this. But I really, again, I enjoy working with students. Lots have contributed to the projects that I do down in Antarctica, and I certainly want to recognize them. All right, so this is sort of my Antarctica 101 kind of introduction, and I'm going to try and give you just a sense of why Antarctica is the way it is and why it's important in Earth systems this way. So perhaps the simplest thing to know is just this slide, right? Antarctica is the coldest, iciest, driest, highest, windiest, brightest, loneliest, the most peaceful, and the least explored continent in the world. And I'll quickly go through why it is all of those things in the next few slides. But if you had to remember one thing, you could say that Antarctica is the most superlative continent in the world. It's all of the most of everything. So just to begin, right, Antarctica, where is it? Well, it's situated down across the South Pole, and it's a continent, meaning it's a landmass under all the ice that's down there. And if you think about it in terms of, what's a comparable size to, it's a little bit bigger than the 48 states. It's a little bit bigger than Australia. I'll pop up in a second down here. right? This is a good sized continent that's down there. And the most common way we orient maps for it is this way, where the prime meridian that goes through Greenwich, England, is oriented sort of up on maps. So we tend to call the left side over here, this would be West Antarctica, and over on this side is East Antarctica. You can see those labeled down here in this bottom right image. The Transantarctic Mountains run across Antarctica. They don't really divide it in half. Actually, about 90% of the ice is over here in East Antarctica, and only about 10% is over here in West Antarctica. But just to give you a few sort of geographic sort of locations that I might mention a few times. We've got the big Transantarctic Mountains. I might mention West Antarctica and East Antarctica. And then the US maintains 3 active research stations year-round down there. The big one being McMurdo Station, which we saw a little bit of in the video I showed. Then we have a station right at the South Pole. And then we have Palmer Station that's over here on what we call the Antarctic Peninsula. And that's kind of fairly close to South America over on that side. So geologically, this is a map of all the major plates on Earth. And I don't know when you last took an Earth science class, but right, the upper, say 100 kilometers or so of Earth's surface is constructed of these plates that are moving away from each other. We see those most prominently in things like the mid-ocean ridges, right? The Atlantic Ocean is slowly getting bigger as that mid-Atlantic ridge is sliding and pushing things apart, and the ocean is growing. Sometimes those plates are colliding with each other, and that's shown by these little triangles that are on here. The Nazca plate is colliding with the South American plate and building the Andes Mountains. Or we've got India is ramming into Asia over here and building up the Himalayas, right? And then sometimes those plates are actually sliding past each other, and you can see those in areas where the arrows are going in opposite directions. The most frequently cited one of those is the San Andreas Fault Zone that's down here in Southern California, right? So there's also kind of an interesting thing to say. Antarctica's also got its own plate. And if you'll notice, it's got mostly these mid-ocean ridges surrounding it. And one reason I like to say Antarctica is sort of the loneliest continent in the world, actually, is that very few other plates interact with it. It's sort of pushing all the other plates away from it, right? And that's just by chance, really. There's a little bit of a strike slip, or what we would call transform boundary, down here by the Antarctic Peninsula, and a little bit of subduction that happens along here. But for the most part, Antarctica doesn't interact with the other plates, and it's actually been sort of tectonically separated from the other plates for quite a long time, which plays a big role in why it's so cold down there. We'll get there. But because Antarctica mostly has all these plates pushing away from it, it actually means geologically not a lot of action happens down there. Because where those plate boundaries are, that's where the volcanoes are and the earthquakes and the new mountains and things, right? By having all those mid-ocean ridges that are way offshore from it, Antarctica doesn't have a lot of young mountains. It has very few earthquakes and really only has a handful of active volcanoes that are down there. Right? It doesn't have a lot of sort of those traditional geologic highlights that are on there. But what is kind of cool is that Antarctica was really in the center of Pangaea, which you can see some of these animations of Pangaea separating down here. Antarctica was in contact with most of the other major continents at that time, and they slowly have pulled away from it. Again, that's part of why it's surrounded by all those mid-ocean ridges. And so it's really central to recreating all of those. And it plays a really interesting role actually in how we really develop the concept of plate tectonics. And it's really actually plays a central role in that, which is neat. So what's really fascinating to me actually is how that geology impacts the climate. So once Antarctica separated from all of those other continents, what it allowed to happen is that basically a number of wind and ocean current patterns set up that go around it. You can see a couple of different wind drifts and current patterns that are on here. And in a nutshell, what that means is that those currents and those wind patterns do a really good job of blocking heat that would normally sort of, it's hotter at the equator, and normally it would sort of move its way towards the poles. These currents do a really effective job of blocking all that heat from getting to the interior of Antarctica. And that's the main reason why it's so cold. Now, in contrast to the Arctic, which is different for a couple of different reasons, But in the Arctic in the summer, it gets much warmer than it ever gets in Antarctica in the summer. And part of that is that there are ocean currents that can get all the way up to the North Pole and kind of help bring heat all the way up there. There are wind currents that can help bring heat from the atmosphere that way. But in Antarctica, there's kind of this blocking pattern that gets set up by these currents. And that's the main reason why Antarctica is so cold today. Sure, it's down near the pole. It gets dark for half the year. We'll talk about that in a couple slides too. But the big reason for it in terms of the main climate is really the geology that set up this pattern where it's separated from all the continents. And what's neat is that happened about 34 million years ago. And this may be a little much for you, but what this slide is showing is a whole lot of data from organisms that live in the bottom of the ocean and make their shells out of the ocean water. And the chemistry of their shells changes depending on the temperature of that ocean water, but also depending on how much ice is on land. And so what's shown on the left here is changes in oxygen isotopes. On the right here are changes in carbon isotopes. Today is up here near the top, and then as we come down this graph, we're going back in time, 20 million years, 30 million years, 40 million years, 50. And what's neat is that when you compile all these data from around the world, from ocean sediment cores from all over the world, you can see a major shift in the chemistry of these shells right at 34 million years ago. When Antarctica finally separates from South America, these currents set up, and we start really changing all of the global climate starts to significantly get colder and colder after that time period. So it's kind of a neat thing that happened right then at 34 million years ago that really shifted global climate. If you think about sort of modern climate, what's wild about Antarctica is that it's actually a desert. It actually only snows the equivalent of about 17 centimeters of water every year. So that would actually be probably more like a meter of snow, but when you melt it down, it'd be 17 centimeters of water. And that's not a lot of water to get every year, right? In Nashville here in a year, we get over a meter of rainfall every year, right? So this is technically a desert across the entire continent. It's just that it's so cold down there, most of it doesn't melt. So all that snow piles up year after year and very little of it melts. And you just make these giant ice sheets that way. Because the snow is white, it reflects a lot of light. Because it's so cold, very few plants and things grow down there. So there's kind of winds blowing around all over the year. And just to give you a little sense, so this map up here on the right, these are all just different weather stations across Antarctica, right? And one thing I like to highlight is there are actually not that many. Some parts of Antarctica, sure, have a number of them, but a lot of parts, there actually isn't a lot of weather data out there. There's a lot of unknown parts of Antarctica still. Down here on the table down here, what I'm showing here is just some data on sort of typical weather kind of climate data for different stations that are down there. Some are out near the coast. And when you're near the coast, like if you're at Mirny or Little America, you'll notice that in the summertime, it actually gets above freezing usually. Right? And the warmest temperatures ever recorded, +8 degrees Celsius, +6 degrees Celsius, right? And, mean summer temperature, pretty close to freezing down there, right? So it warms up. You might get a little bit of melt when you're near the coast. But once you get inland, so all these other stations are inland in here. So take the South Pole, right? The warmest it's ever been recorded at the South Pole is still -14 degrees C. Like it never gets close to freezing up there. And really all the snow that falls there never melts, right? And so perhaps the takeaway sort of for the modern climate is that out near the coast of Antarctica, you're gonna get a little bit of meltwater. Once you get inland, very little meltwater is gonna happen at all. And because Antarctica is down at the pole, you do get these kind of amazing solar cycles and sort of daily annual weather cycles, meaning that, when it's summer down in Antarctica, which southern hemisphere, their seasons are switched from ours, right? So summer for them starts December 21st, right? And in December 24th at the South Pole, you're gonna have daylight all 24 hours a day. In fact, you're gonna have daylight for about 4 months straight. So beginning around November 1st, all through December and January, and then till sometime towards the end of February, the sun will finally start to go down. right? And so if you see that in the temperature data, you know, it starts to warm up and kind of peaks around December 21st or so. And then the sun starts getting a little lower in the sky and the temperatures start to drop down. Now in March and April, the sun will actually kind of just come above the horizon and you'd get a little bit of daylight and a little bit of darkness. But then around the end of April, so all of May, June, July, August, basically, it's going to be dark. And you can see in the temperature data, it just stays cold through all that winter time. But then, you know, in the beginning of September or so, the sun starts to creep back up, and in October, and then by November, the sun's back up fully and the temperatures are going to start to rise again. So under that sort of climate regime, when it snows, very little of it melts and it just piles up thicker and thicker and thicker. And in some places, it actually gets to be thousands of meters, so a couple kilometers thick. So just to give you a sense of Antarctica, I said it's the highest continent. Well, that's really because of all this ice on it. But you can see in the data in here, it's a little hard to see that scale bar, but a lot of Antarctica is actually over 4,000 meters in elevation. And sure, that's the ice, the elevation, but that's the surface of the continent down there, right? So we're talking about huge amounts of ice. Now you might want to say, all right, but what about, where's the rock underneath there? How much of that is rock? And it's true that in some parts of Antarctica, so this is an image now showing what's the elevation of the bedrock underneath all that ice. And actually, some parts of that bedrock are a couple thousand meters in elevation. So maybe the ice is only 2,000 meters thick. And you'll also see that some parts of Antarctica, especially here in West Antarctica, the elevation, if it's blue down here, it's actually below sea level. So if you took off all the ice there, there would be some open ocean in here. In fact, West Antarctica is a little different that way, and that most of it would be below sea level if you took off all the ice. East Antarctica, though, that's where the main continent is, and that's where most of it would be above sea level if you took off all the ice. So if you have the surface and you have the bedrock, well, then you can subtract those things and get the thickness of the ice that's out of there. So here's a couple different data sets of ice. There's these older data that came out in 2000 called BedMap. They just updated BedMap 2 a couple of years ago, and you can see it's got a higher resolution, better data set. But you can see parts of the ice are really over 4,000 meters thick. That's all the red stuff in here, right? The yellows are kind of around 2,000. The greens maybe around 1,000 meters. And the main point I think I would emphasize is that's a lot of ice, right? Mean thickness is a little over 2,000 meters. So lots of ice. So I keep calling it snow and I keep calling it ice, and it's kind of fun to think about the difference of all of that. And so first, you know, what's precipitating out of the sky down there is just snow. So it's all these little snowflakes, right? They've got these nice little crystals and fun patterns, right? But if that snow doesn't melt from one year and more snow piles on top of it the next year, then it starts to get compressed under its own weight. And once you get somewhere around 10 meters or so of snow, under its own weight, it will actually metamorphose and compress into ice. And the difference to us in earth science is that when it's snow, air can actually move between all the little gaps in the snowflakes, and it will actually exchange air with the atmosphere that way. When it becomes ice, it's gotten so compressed, and I can't quite do this with my hands very well, but it's gotten so compressed that those air gaps are now trapped as air bubbles in the ice, and it can't exchange with the atmosphere anymore. So if you go to your freezer today, grab an ice cube out of it, and if you look at it, it'll be a little gray, and if you can zoom way in on it, you'll actually notice a lot of that little gray comes because there actually are little air bubbles trapped in all the ice. If you heat up some water, get some warm water, drop an ice cube in it, put your ear next to it, you'll actually hear those air bubbles popping and crackling and crinkling as they pop out of the ice there. And so that's kind of the technical distinction between snow and ice. So on average, I mean, this is a ballpark, you need about 10 meters of snow will compress into ice. And then the other nice thing is, once you get about 10 meters of ice, under its own weight, that ice will start to deform and flow, and then it's called a glacier, right? Or if it's a big glacier that covers an entire continent, well, then we call it an ice sheet. But that's kind of, there's sort of a transition from snow to ice to glacier that way. And so this is kind of my crude drawing here, but you've got a bunch of snowfall, it piles up, becomes an ice, becomes a glacier, starts flowing. In general, it's kind of just flowing downhill due to gravity. Really, it's flowing from where it's thicker to where it's thinner. But again, on average, that's usually from the interior out towards the coast. And the ice in Antarctica is so thick that when it reaches the coast, it doesn't just break off there. It melts a little bit at the coast, but it's still so thick that it continues to flow for hundreds of kilometers out into the ocean, into what we call these big ice shelves. And then it breaks off icebergs from that. And that's kind of the main way that it loses mass. So if Antarctica is not changing size from year to year, if it's kind of balanced that way, then all the snowfall that falls and doesn't melt and sticks around would be balanced by all the icebergs that break off and flow away. But as we know, there's lots of data thinking about Antarctica's losing mass, and that's because more icebergs are breaking off of it than snow is falling, that in terms of the water equivalent of all of that mass that's lost every year. So, and that's the other thing I want to emphasize on here is that's a little different than sea ice, which is really just frozen ocean, right? Sea ice is just the water in the ocean freezing. These ice shelves, the ice sheet, they all originated as snow on land that compiled and compressed into ice and then flowed out into the ocean. So this is probably a better schematic of it. I sort of like my crude hand-drawn one. And I also like this because Antarctica is kind of unique in the way that it spits out these giant ice shelves. In Greenland, which is the other big ice sheet we have in the world today, it pretty much stops right at the ocean, and icebergs are breaking off of it, but it doesn't extend these gigantic ice shelves at all. Maybe a couple 100 meters or so of an ice shelf in Greenland. But in Antarctica, the Ross Ice Shelf is probably 300-400 kilometers long. It's this giant tongue sticking out under there. And the other thing I like to talk about Antarctica just quickly is actually, you think it's all frozen, but what's wild is that there are actually hundreds of liquid lakes underneath the ice. And so this is a map on the left showing a bunch of locations of all of the lakes. And this is a little schematic of it. The basic idea is that, under a few kilometers of ice, you might actually be above the pressure melting point of water, and you can have liquid water down there. And some of these lakes may have been liquid for tens of millions of years. So Antarctica's had ice sheets for the past 34 million years. They've changed in size over time, but especially some of these lakes near the interior, they may have actually been lakes for, 20, 30 million years and just covered by ice. And they're kind of a fun, people are really interested to explore these. There are lots of drilling operations to try and drill down to them and collect samples from them without contaminating them is the real challenge. There's been a new project called SALSA, which is a great acronym, and it's a subglacial Antarctic lake exploration project. They've been recovering some samples from these things. And I like to think it's kind of as close to visiting another planet as you can get here on Earth, because this is some part of Earth that really hasn't seen the atmosphere in perhaps 34 million years. And who knows what's living down there today. All right, and the other thing I like to think about when we do sort of an introduction to Antarctica is just, how much water are we talking about? How much ice are we talking about? So this is a simple schematic of all the water on Earth. So over here, here's all the water. Well, 90% of the water on Earth is in the ocean. Salty, can't really drink it unless we desalinate it, right? So about 3%, a little less than 3% is fresh water. So if you break out that fresh water, all right, about 3/4 of it is on the surface, and about 1/4 of it is down below ground. It's groundwater that we would call it, right? But of that surface water, most of that surface water is frozen, right? So look at this, over 99% of that surface water is frozen in ice sheets and glaciers. So it's kind of wild to think about, if you've ever been to Chicago and you've gone out to Lake Michigan, there's some big freshwater lakes out there in the world. They're only about 1/3% of all the fresh water on the surface of Earth, right? For as big as they are, there's still nothing in comparison to Antarctica. And when you look at all of this ice that's down here, about 90% of that is down in Antarctica. So again, like how much ice is that? Well, if you could melt all of Antarctica, you'd raise global sea levels by about 58 meters. Right? So somewhere on the order of about 180, 190 feet, right? Greenland, on the other hand, it's about 10% as big as Antarctica. It's only about 6 meters of sea level equivalent that you get in melted all of Greenland. And you think about all the other glaciers and mountains and things, they're not even a full meter or so of ice that's down there. So, right, this is what most of Antarctica looks like. This is us flying across the transantarctics. There are just a few mountain peaks and things that stick up there. 98% of Antarctica is covered in ice. But you may have noticed in that video that I showed, I wasn't on the ice a whole lot. I was in, it's just a helicopter. But I go to the parts of Antarctica that are actually the valleys and the mountain peaks that stick up above the ice. And when the ice sheet was thicker in the past, when it was bigger, it would have come into this valley and covered parts of it. But now that the ice sheet is a little bit thinner, and I don't mean in the last 100 years due to human activity, this is a change in the last 20,000 years that has exposed this. But this is what it looks like now. And I like to do kind of a fun, I'm one ahead of myself, right? In this environment, it's really cold. It's always below freezing here. Mean annual temperature in that valley is about -23 degrees C. It's wonderful when the sun is up the whole time, but it's still, on the order of -10, -15 degrees C when we're down there. So nothing is melting. It's too cold for anything to grow. You just have all these rocks and nothing really is happening that fast because not much is happening. I mean, the wind is blowing and the rocks are warming and cooling. So sometimes you get these amazing thermal contraction cracks that form rocks. I didn't stack these rocks up at all. They're just forming that way. They're getting all these amazing cracks and wind-blown features in them. And so not a whole lot happens here. It's pretty wild. And I like to do this kind of thought experiment, right? So as an earth scientist, I think a lot about long time scales. So, how old is the Earth? All right, well, the Earth, here's a geologic time scale. It's like 4.54 billion years old, right? And so here's a geologic time scale. This is the scale here. So this says 4.5 billion years coming all the way up to today where we are. Right? I like this kind of more cartoony, colorful, spirally one as well. But then it's kind of fun to think about, when did land plants evolve? And what did the surface of the continents look like before this? So I don't know how much earth science you've had, but I'll break some of this out for you. So here's that same time scale. And then just the last 540 million years are broken out here. So a little more than 10% of it, right? This is like 13% of Earth's history. And really, what the geologic record shows us is that this last 13%, that's 540 million years or so, that's when we have kind of complex life here on Earth, right? Really, life hasn't been on Earth all that long. We can say, all right, we've got rocks that are at least this old. We've got some bacteria that go back to about 3.6 billion years. There seems to be a big oxygen event. We get enough algae and things that are pumping huge amounts of oxygen into the atmosphere around 2 billion years, right? You think about the big extinction at the end of the Permian that happened there. This is actually before the dinosaur extinction. There's a bigger extinction than that. And then it's kind of fun to think, all right, so in this last 540 million, that's when complex life comes around, right? The Ordovician down here is when fish come around and the first land plants are evolving, somewhere around 475 million years ago, right? Ferns and things are coming around 350 million years. But mammals and flowers, they're really only in the last 200 million years or so. Grasses are actually fairly young. They're only like 2 million years old. Right? So the fun thought experiment, all right, so if land plants haven't been around for, just say they came about the last 10% of Earth's history, what did Earth look like for that first 90%? Well, it kind of looked like this. Right? I mean, we're walking around and it's just barren and rocky. I always like to say it's as close to being on the moon as I'll ever be able to get, right? This is what the moon looks like, except I don't have to wear a spacesuit and I can breathe the air, right? But the moon is just barren and rocky. Nothing growing out there. tease. It's kind of a geologist's paradise, right? There's nothing in the way of me and my rocks, but it's also pretty eerie, right? So as we're out on and doing our field work and collecting these samples, it's a really unique experience down there. All right, so maybe just to talk a little bit about my research. I know I've gone on a little bit. I'm always slower with this than I want to be, but in terms of my motivations for my research, I'm really interested in like how old are the glacial deposits. I'm focusing on Antarctica here, right? In the Antarctic, these dry valleys, these places that are stick up above the ice sheet, right? And what's the former extent? So like how far into these valleys did they? I'm really interested in basically like the timing of past ice ages. How has the ice sheet changed over time? When was it bigger? When was it smaller? How much bigger? How much smaller? Right? I get to do this all over the world, but for now we're focusing on Antarctica, right? And the other kind of fun thing is, well, these are such weird environments. They're as closer to the moon or Mars. In fact, they go down and test the Mars rovers down in these kind of valleys in Antarctica. And so it's important to understand like what kind of landscapes are these? What's active in this landscape? What's going on, right? It's also kind of fun to think about, although this is outside of my realm, but like what kind of life actually exists down here? Because I will say, as much as it's barren down here, it's not sterile. There actually is a lot of microscopic life down here. And it's really wild that life persists even in these extreme environments and gets people really excited thinking about maybe there's life on Mars. In fact, there was just a thing about subglacial lakes under the ice caps of Mars that they think they have identified now, which is really cool, that might have life in them. So ultimately, my research, I'm interested in how have things changed, but the ultimate goal for this is to think, all right, what is Antarctica going to do in the future? And these are a couple of model simulations here from a couple of folks named Rob DeCanto and Dave Pollard. And on the left, it's showing kind of a low carbon emissions model where we don't emit very much carbon, but the ice sheet is still thinning and losing some mass. On the right over here, unfortunately, is the sort of business as usual carbon emissions model. And you can see, you know, by 2500, lots of West Antarctica is just totally gone, right? And ultimately, you know, what we want to know as a sort of a scientific community is, well, what scenarios, where are we headed, right? How much is sea level going to rise, right? And these guys conclude by 2100, even in the best case scenarios, we're looking at least a meter of sea level rise and maybe more than 15 meters. I will say this is just one model, all right? There are lots of different models, and some folks predict 3 meters of sea level rise by 2100. And then it's fun to think, well, how do we test these models? Well, that's kind of more where I come in. I'm much more the historian, right? I want to understand how has it behaved in the past. So ultimately, we want to know how have things changed in the past. This is a concept that we call uniformitarianism, right? We look at things like what's active today, and that helps us understand the past, but also what's happened in the past helps us understand what's happening today, and then lets us predict the future. So there's a simple phrase in earth science, you know, that the present is the key to the past, right? That's the title of this book that came out a few years ago. Present the key to the past, or is the past the key to the present, right? And then you think, well, maybe the past is the key to the future, because ultimately understanding how the ice sheet has changed in the past, and if we can accurately recreate that, then we have some trust in our models that they can create the future pretty well. So these guys, Dave Pollard, Rob DeCanto, they've created a whole bunch of models to model the past behavior of Antarctica. This one on the left is going from about 1.7 to about 6 million years ago. This one on the right is going from about 400,000 years ago all the way up to today. And so my data help them constrain these models. I'm able to tell them, hey, the ice sheet needs to be this thick at this spot on these dates. And there are lots of people like me who go all over Antarctica to try and date these things and figure out how they're changing over time that contribute to something like this. But if these models can pretty accurately recreate the past, then we have a pretty good idea that they're going to run forward into the future pretty well. And just to perhaps emphasize, right, I know 1 meter of sea level rise doesn't sound like a lot, but here are a couple of images just sort of showing what would be the change in the coastlines along Florida and the eastern seaboard if there was 1 meter of sea level rise, right? And for these states, right, 10% of their land area would get submerged. Talking about 1.5 million people that would have to be displaced from this part of the world, and more as population grows before 2100, right? So there's significant interest in understanding all of this. So in the next few minutes, I'll talk quickly about like, what do I really do in Elm Valley and what am I trying to do and sort of what is my lab like? So this is from my most recent project, and it was down in Ong Valley, which is sort of in the central part of the Transantarctic Mountains. This is just sort of a little blow up of the map and what it looks like. It's one of these dry valleys. It's most of the pictures you've seen have been from there. And what's neat is here's the Argosy Glacier today, but in the past it was thicker, in which case it came deeper into the valley here and left behind 3 really distinct glacial units. And maybe you can see there's sort of a younger unit that's darker over here. There's a middle unit that's kind of middle colored, and then there's a much lighter colored old unit over here. I'll put those back up. And what's neat is, you know, based on the geologic maps that existed, this was just sort of mapped as like, it's got some glacial deposits. No one had really done any work in here before we landed. And so we were able to map out totally unmapped areas and determine how old they are. Just to give you a little sense of what the field work is like, again, here are a couple of other videos. So when we go to a place like this, you saw some of this in the video I showed, right? But we were collecting rock and soil samples to try and date those glacial deposits. Underneath some of those deposits, there's actually buried ice that we were drilling into with a drill core to collect. 1, to understand how old is that ice, and 2, to look at the climate data that ice contains, right? As I was describing earlier, when snow falls and compresses down into ice, it traps those air bubbles, and it actually traps information then about what former atmospheres were like. This is how we know what the level of greenhouse gases used to be for the past 800,000 years. So we want to use that ice as an archive of past data. But we're also collecting samples from rocks and soil and trying to characterize as much data out of this to understand as much about this valley as we can. So a lot of my work focuses on getting the age of when the glacier deposited these rocks, because that's when it tells me this is when the glacier was at this site. And so what I use are actually isotopes of things like beryllium and aluminum and neon that build up in rock samples over time. And then I bring those rock samples back to my lab, isolate minerals out of them, analyze those isotopes, and they tell me about how long that rock's been on the surface. So here are a couple of boulders we sampled. This one's about 2 million years old, 2 million years old. Here's a big map that's got too many numbers on it. But basically, we get some ages for this young drift that's around 10 to 40,000 years old. We get ages in that middle drift that's around 2 million years old. And then we get ages for this oldest drift that are actually upwards of about 7 million years old. So again, Antarctica's got this incredible record of glacial history recorded on it that we don't find anything like that in North America that's 7 million years old. It's too wet. There's too many plants, there's too many ants and gophers and things digging things in, where that stuff just gets erased. But down in Antarctica, where it's so cold and dry, that stuff sticks around for 7 million years as if it was there yesterday. It's wild. We collect a lot of samples from the rock in the area. One, to look at how quickly is it changing through time. So erosion rates, like how quickly is the rock lowering? And then I'm also trying to look at how is it weathering. So I look at these chemical indexes of alteration and things down there. These data may not mean a ton to you, but just trying to illustrate, we collect a bunch of rock samples to understand how quickly is the environment changing in this really cold and dry climate. This is projects actually the students from the School of Science and Math at Vanderbilt have been helping a lot with these kind of projects, which is I want to look at the source of the till in Antarctica. And to do that, we're collecting big Ziploc bags of all of that sediment that the glacier brought. That's called till. We isolate these minerals called zircon from them. Here's a scanning electron microscope image of zircon. And we then date those zircon with a laser system, and we date them with uranium and lead isotopes. So we know when that zircon mineral crystallized. But if we can find a couple hundred zircon from a till, we get a whole bunch of ages. So this is just a graph showing all the different ages we got. going from 0 here up to 4 billion years old. So we actually find a bunch of basically 3 billion year old grains of sand, which is really, again, I love the sort of big time things, right? The little grain of sand that's just been bouncing around Earth's surface for 3 billion years. Somehow it ended up in Antarctica in my bag, and then we pulled it out. But by basically looking to say, hey, do these oldest and middle and youngest tills, do they have the same distribution of zircon grains? Tells me if they came from the same source of material underneath the ice. And the short answer here is yes, they do have the same distribution, and they appear to have come from the same source, meaning that glacier has been flowing the same way for about 7 million years. And so it's, some of that's just sort of a snapshot of the work that we're doing down there. So it's kind of wild. Again, here's Ong Valley. We've got tills that record the glacial history up to about 7 million years. It's actually, that part of Antarctica has only changed in elevation about 200 meters in those 7 million years. This is a part of Antarctica. So one of the other take-home messages sometimes is parts of Antarctica are changing really fast. Parts of it are changing really slowly, and we need to understand that to be able to better predict what's going to happen in the next 100 years, right? Till's as old as 7 million years old. The glacier seems to be flowing the same patterns. It's changing really slowly. It's weathering in kind of unique ways. I didn't get into much of the chemical index of alteration data, but it's unlike most other environments on Earth because it's so cold and dry down there. So there's really fun things we get to learn and do as sort of some of the first geologists to get into this valley to be able to work on that area. So I'll stop there. I know I've taken up quite a bit of time. I've rambled a lot, but I'm certainly happy to answer questions. I've got lots of pictures of what camp was like and different things if you're curious to learn more about that.